Okay, everyone, so in this video, we're going to talk just a little bit more about Chapter 9, Electrons and Atoms, and the Periodic Table. In this video, we're going to focus on the first learning objective that I have presented to you, which is to compare and contrast differences between the orbits in the Bohr model of the atom and the orbitals in the quantum mechanical model of the atom. I'm kind of using key characteristics from each model, where they come from, who founded them, why each has its own merits, and so on and so forth. So that's where we're headed. So, forewarning. Today gets a bit esoteric. We're kind of leaving the chemistry realm a little bit. We're still talking about electrons. However, we're going to talk about the nature of electrons. So this can feel a bit like a philosophy debate almost. So it's going to be a little uncomfortable. It's going to feel weird. So sit down, buckle up, and be ready to open your mind about the nature of the world around you. I sound like a guru or something. So I could teach a yoga class. So I'm just teasing, guys. It's the opposite of chemistry usually, right? So anyways, kind of remember back to our first couple of classes. I kind of mentioned in a sly way that electrons aren't real, so therefore the universe isn't real, and we all live in a simulation. Who cares about anything anyways, right? I don't know who hit the pandemic button and ran that line of code, but here we are in 2020, right? Oh, it's 2021. Oh my God, brain slip. This is the world we live in. So anyways, the universe kind of isn't real. Well, it's simulation time, baby. We're going to talk about why I think the world feels like a simulation. By the end of this, you'll kind of understand what I mean. So in this chapter, we're going to spend some time going into the true nature of electrons and what atoms really look like. So this will help explain a bit of the characteristics we ended up seeing in chapter 10. We're back to modeling again, our favorite thing. Here we are. But in chapter 4, we talked about the nuclear model of the atom, and we kind of left it there. That there's this small, dense nucleus at the center of an atom, where most of the mass of the atom lies. This nucleus contains positively charged protons and neutrally charged neutrons. Atoms are mostly empty space, as we might remember. That means that there's this large area around the nucleus called the electron cloud, where those negatively charged electrons are flying around the atom. They don't have very much mass to them, so they don't take up much of the mass of the atom. However, this is still really vague. It doesn't really tell us anything. And we've learned so much more about electrons then and what they can do as scientists, and this has influenced an update of the model of the atom. So really what got people thinking was how the atom interacted with light. So let me get me out of the way here a little bit. So the nuclear model of the atom, as we had been discussing it, was a little too vague for our understanding of electrons. What scientists couldn't figure out was how we could explain electronic emission spectra. So electronic emission spectra are an experiment run with this setup you kind of see over here. So the idea is that by exciting an atom and interacting with its electrons almost using energy, by passing that through a slit and breaking that very fine line of light with a prism, what we found is that atoms have each a unique spectrum of light that comes out of there. And the nuclear model of the atom didn't really explain this. You know why? Because we see light around us all the time, but we don't see anything in the end. It's just kind of around us. However, white light, what we usually see, what we think of as light, is actually the full range of colors in the rainbow. So it's the full range of the electromagnetic spectrum in the in the visible light section. So even though we don't see any colors when we see light, what we see is what we actually are seeing is that we've got all the colors. We're just kind of interpreting all of the colors interacting with each other as a white light. So that's why it's so interesting that in the end, we have these separate bands of light coming from our atoms. Kind of doesn't make sense. If if there wasn't something weird happening, we should just see the prism breaking everything into a full rainbow. That's interesting. Why isn't it this way? Well, chemists set off, they said, we're going to figure this out. We're going to come up with a model of the atom to explain why this happens, right? Because in here, if this is just hydrogen gas, the only thing that's in there are hydrogen atoms. And the only thing that's producing all of these colors at the edge and onto our film to create our emission spectrum are hydrogen atoms. So there must be something going on with our atom that's causing this. So this led us to the Bohr model of the atom. So the Bohr model of the atom, it kind of looks familiar. I did use a bit of the Bohr model of the atom last chapter to talk about core versus valence electrons. So it was Niels Bohr who nailed down a model of the atom to help explain that hydrogen emission spectrum. So what he decided is that electrons must exist in exact rings around the nucleus. And each of these rings had an energy level. And when electrons would take in energy, they would jump the ring that they were in, and they would become what we call excited. And then things don't like to be excited. They like to be in the ground state, which is what we call the non-excited state, the ground state. It does what we call relaxation and falls back down to its original orbit, to its original ring. And when it does that, it gives off a specific wavelength of light. Because light in the end is just a packet of energy. So what we're seeing is that we have energy coming in, it makes the electron excited, it jumps rings, and then when it goes back down to its original ring, it gives off a specific wavelength of light, depending upon the energy level there. Energy levels correspond to different wavelengths of light. So what's happening here is our electrons are jumping rings. They give off a specific wavelength of light, depending upon the distance between these rings. And that's why we see these individual lines in the spectra, is what Niels Bohr said. So we call these rings orbits. So they are individual separate rings. They aren't saying like everything within the ring. I'm talking about that line exactly of the ring. And what he said is that these orbits, I'll call them orbits from here on out, kind of like how planets orbit the sun. We'll call these orbits because the electrons are orbiting the nucleus. So these orbits are these separate rings in the electron cloud. And electrons can only exist on these specific rings. So that's what we call discrete, something that is separate from each other, not continuous. So all of the colors together is continuous. We can't see where one color ends and the next begins. However, these individual bands, those are discrete. They're separate from each other. Red, this red over here is definitely separate from this blue, green is definitely separate from this violet. This n equals 1 ring, this inner ring, is separate from this number 2 ring. Remember, their electrons can only exist on that circle itself. And so he was saying on these orbits that those electrons transitioning between orbits when they came back down from their excited state is what's giving off these colors of light. And because these orbits are so separately apart in these specific fixed positions, each atom must give off a different kind of light. Different color of light, I should say. So that's what causes the individual bands, because there's only a specific difference in energy between each ring, and each of those differences in energy corresponds to a specific wavelength of light, because light is just energy. So it's saying this is the energy that is between those two rings. So light is energy, right? It gives plants the energy for life, to do everything that we need to make the oxygen for us to live in the end. So we need light to live. Here, we're doing the same thing. Light is just energy. Kind of hard to wrap your head around, right? It's a little weird. So this explains the hydrogen emission spectrum. This is the Bohr model of the atom, and it has orbits, these rings where the electrons must lie specifically on the ring, and this explains the electronic emission spectrum for hydrogen. Okay, so the Bohr model of the atom seems pretty reasonable for what we expect in atoms, what we talked about in class so far. I always think of Jimmy Neutron, that's kind of the model of the atom they used to make the logo for that. I interned at the nuclear power plant. Everything that we have has the Bohr model of the atom as their model everywhere. Those electrons in rings around a nucleus. So where's this simulation, Emily? What the heck are we talking about? Well, here's the deal. Bohr's model only explained the hydrogen emission spectrum, not the spectrum of atoms with more electrons. It didn't explain anything else. With all of those fine lines, like if we go back and look at neon here, for example, it couldn't predict neon. It had no idea why neon was doing what it was doing. So we needed to try something else. And our new friend, my favorite, he's one of my favorite, our new friend Erwin Schrodinger had something to say about this. And this is what he said. His radical idea. Well, the radical ideas of quantum mechanics. Schrodinger's the father of quantum mechanics. Here's the deal. I've been telling you electrons are particles this whole time. They're not. Well, not exactly, okay? So I didn't lie to you, but I only half lied, okay? So electrons kind of aren't there until we look at them and we choose to measure them, okay? So I've got a video for you guys to watch. You should go watch part 1 and part 2 here on YouTube. Come back, finish watching me here. I'm not going to play the video on this recording. I'm pretty sure there'd be some sort of YouTube, I'm not allowed to do that, takedown of using someone else's video in the middle of mine. So please go watch the YouTube video I have listed in the slides here and come back. It's going to give you some animated visualizations of how this works. So go watch it. Go watch it. Are you back? Did you come back? What's up? Hey, how's it going? So back to Emily's explanation of the quantum mechanical model of the atom. So the idea here is that electrons are kind of a particle and a wave at the same time. So yes, they're a particle that has mass, exists, and we know what it is, that kind of a deal. It's got a negative charge. However, they don't actually nail down their location and choose where they're going to exist until we observe them. Until that point, they exist as a wave of probabilities. So it's all these different places that the electron could be, but we don't know where it is, and we don't know that until we measure it, okay? So that's how it works. So it's a particle, yes, but it's a wave until we make it choose to be a particle and choose a location. Everyone's favorite scientist, he's a good one, but I'm more quantum mechanical model kind of gal myself. Albert Einstein hated this theory. He thought it was absolute garbage. He did not agree with anything they had to say with it. He thought he was like worse off in his life for having heard the quantum mechanical model. However, the thing is the quantum mechanical model has such explanatory power, it's crazy. It is the foundation of modern chemistry. It explains almost everything out there. And you know what Schrodinger's response to Einstein was? If you don't think quantum mechanics is a good theory, you must not understand it. And you know, we're here talking about the quantum mechanical model of the atom all these years later. It's just kind of nice to remember that even the titans in science can be wrong, just like Einstein. So this is the foundation here of modern chemistry. This is what we have learned. The quantum mechanical model here, however, with this whole idea that electrons aren't exactly particles all the time, runs us into an issue with the Bohr model we just talked about, right? We said that those electrons had to exist exactly in those rings, and going between those rings causes a transition. electrons don't always exist, how are they supposed to constantly orbit and transition? So how do we think about this in the new quantum mechanical model? So in the quantum mechanical model of the atom, we basically choose to use the principle that electrons are both particles and waves. And that allows us to basically kind of create an electron cloud. This is really what starts to make it feel like a cloud to me, is that we kind of basically consider all of the probable locations where an electron might exist around the nucleus. So rather than thinking of it as that individual, specific, separate ring that electron specifically has to stay in and orbit and is there and just jumps back and forth to those different rings, those things there. It's more like now we have that cloud, and an electron's going to probably exist somewhere in here. We can't nail it down, but I can tell you where it's more likely to be than where it's not likely to be. It's got favorite places to hang out. It's got a favorite watering hole. However, sometimes it gets out and tries other stuff. So that's kind of what we're modeling here. So instead of calling them orbits, we call these maps of probabilities orbitals. So orbits and orbitals are very separate, very distinct, very different from each other. I want you to know the difference, and I want you to say which one you mean when you're saying it. So if you're talking to me about the quantum mechanical model, I'm expecting to hear orbital because we're talking about orbitals. So if you say orbit, I'm probably going to ask you because I'm going to not really totally know what you're talking about. So quantum mechanical model has orbitals. Bohr's model of the atom has the orbits. So you can kind of think it. The planets travel in more of a specific line around, so they orbit the sun. So you might think of orbits with the Bohr's model like the planets, whereas here the orbitals are an expansion of that. It's a longer word. It's an expansion. Maybe something to remember the difference by. So these orbitals are like probability maps that tell us the likelihood of where an electron might lie. So you can see in this picture here, the nucleus would be considered where all three of those axes intersect. And so you can see there's lots and lots of blue dots here at the center and a lot less blue dots here around at the edges. So each of these blue dots represents like a high likelihood that an electron exists. It's almost like if you think about like you leave a camera on a time-lapse photo and we see all the different places that an electron pops up over a specific amount of time. That's kind of what we got going on here. That's what it's showing us, that it shows up here a lot and it doesn't show up around these edges quite so much. So electrons, again, are more likely to lie generally in towards the nucleus, where the attraction's the greatest. They want to be near that positive charge. And this still explains the electronic emission spectra because each orbital has a specific amount of energy associated with it. So we're going to think about maybe those electrons jumping between orbitals and jumping between spaces and probabilities of existing rather than jumping between these orbits or rings. So these are more like shells and layers around the nucleus rather than rings. It kind of goes from 2D almost. It can only orbit in like one direction at a time versus it can be anywhere around that nucleus at any point in time in the quantum mechanical model. So these are some pictures of some orbitals. So they can be kind of hard to think of and they're a little kind of funky, but this is what we figured out when we use observational techniques to look at the probability of where electrons lie, or to look at where electrons lie and then extrapolate the probabilities from there. So this is what we call an S-shaped orbital. So an S-shaped orbital just looks like a sphere around the center of the atom there. Again, in towards the center, we have a higher probability of the electron lying close to the nucleus and out towards the edge here. So it's only made up of one shape. It's just one big sphere. Over here we have p orbitals. So these are what we call p orbitals. So we'll find out next video that orbitals are named by both a letter and a number. We're just talking about the letters here to get a feel for the shape of these orbitals, okay? So here we're talking about p orbitals. So p orbitals kind of look like dumbbells. You can see that there's a high likelihood in the center of the dumbbell here for those electrons to lie where there are lots of dots. And it's not very likely they're close to the center of the atom. So there are kind of three little spaces associated with p orbitals. So we might call all of this a p orbital, or we might call one of these individually a p orbital as well. It gets a little confusing. So you group them together to make the whole of the 2p orbitals, but there's a 2px, 2py, and 2pz orbital technically. You don't need to know the px, py, pz, none of that. You just need to generally understand the shape of the orbital and understand that there are three kind of mini orbitals that make up the one big 2p orbital. Down here we have the d orbitals. So these are the d orbitals. There are 5 of them. So there's one s orbital. There are 3 p orbitals, and there are 5 d orbitals. Remember, those numbers, they don't correlate with what I'm saying here. I'm counting the number that we see. Those mean something else that we'll find out next time. So I'm just counting the number of pictures I see. So there is one s orbital pictured here. There are 3 p orbitals to make up one p orbital. And here there are 3d or 5d orbitals to make up one d orbital. So the d orbitals spread the electrons even further away from the nucleus. So the d orbitals take them into a further space away from the nucleus. So it kind of looks like these little flower petal shapes, like a 4-leaf clover, just lined up different ways compared to those x, y, and z axes in a 3D space. And then it also has this cool donut dumbbell looking shaped one. Again, this is all figured out experimentally, that this is the probability as to where these things lie, and we have lots of mathematical models proving these things. So the d orbital takes all 5 of these to make up a d orbital. So one d orbital actually has 5 little orbitals underneath it. And they look like this. So what do we do with these? Okay, I went on a rant about orbitals. Electrons don't exist. Where are we? So the orbitals just give us maps to place the electrons into based on a set of guidelines. In a minute here, we'll talk about the set of guidelines in the next video. And so we can tell which electrons, once we do this, are the valence electrons rather than just having a number. We can point to a general location on the outside where these valence electrons are likely to lie. We can tell which orbitals they're in. And the quantum mechanical model, as I mentioned before, has great explanatory power. Unlimited power! So the quantum mechanical model has this great explanatory power. So depending upon how the electrons fill the orbitals, atoms tend to participate in different kinds of chemistry. And in the end, we'll see that this is why the periodic table makes sense, okay? We lined it up based upon the number of protons, but in the end, it was actually the electrons that dictated why the periodic table is set up the way it is. The quantum mechanical model explains the size of atoms compared to each other. All atoms are different sizes. It explains magnetic properties, like why O2 is magnetic. Liquid oxygen is magnetic. It'll stick inside a magnet, even though it's a liquid. It's kind of cool. If you haven't seen a video of it, please go look it up. It's really cool. It also explains how metallic something is. It explains how the electrons behave in metals and why those transition metals behave so funny and form all these different ions. It explains that electronegativity we were talking about, why certain atoms want to pull the electrons to themselves more than others do, and why others are willing to give their electrons up. And it also talks about how hard it is to pull an electron from an atom. It explains that too. It explains so much once we come down to it. It explains almost everything. But we haven't explained everything yet. We're still studying. We still don't know. We're still nailing it down. So believing that electrons exist in this wave-particle duality where it's not exactly a wave, it's not exactly a particle, and it's this set of probabilities until it's fully observed and until it's observed, and this truly explains the way the world works around us. It does. There are still things that we're editing the model for, don't get me wrong, but it does way stinking better than Bohr's model does. It does way better than the nuclear model of the atom. It does way better than whatever the heck Einstein came up with that we're not even lecturing over. It does way better than that plum pudding model that we saw way back in the day, or even thinking of the atom as a hard sphere like the Greeks did. This is the one that we have that explains the most so far, almost everything. If we can find that grand unifying theory between physics, we'll be able to unify quantum mechanics with what we see in the real world and how physics acts on that large scale of the universe. And once we've done that, we can prove we're living in a simulation. It's all math that explains the world around us. I'm teasing about the simulation, don't get me wrong, but it's so beautiful when you can look at the mathematics. You can see why the world around us works the way it does, and it's all because we don't believe that electrons actually exist. Now, how's that for a philosophy lesson from your chemistry professor today? I don't think I did too bad, so please let me know if you have any questions. In the next video, we're going to talk a bit more about how these electrons go into the orbitals, what rules they follow, and how that's kind of affected some of the things we learned, but we didn't quite know that yet. So